Hello, everybody. Welcome. My name is Chris Skrinak. I am a partner solutions architect and the global machine learning segment lead for the Amazon Partner Network. I'm really glad you can make it to this session on PyTorch. It is a topic I am passionate about. And where it sits in the machine learning stack is sort of right at that fundamental grassroots layer. Starting from the bottom up, as you know, we have our infrastructure, our compute structure. You know, one level that's kind of beneath this is the storage structure, right? In machine learning, I frequently say data rights code. That is the fundamental software engineering change that we're experiencing right now in this revolution. Unlike in the sort of the old days, which were 3 years ago, you're really looking at data now to write highly nuanced functions that were either difficult or impossible to do. And that's all thanks to the advent of some changes in the way that we do backpropagation, for example, in deep learning models, but also the hardware, right? But you don't have anything unless you have data. This is a situation where the data writes the code. You need an infrastructure like the kind that's provided by S3 and the variety of database systems, purpose-driven database systems that we have, including relational, graph, in-memory databases, even blockchain. So that's that fundamental layer. And here we take a very non-prescriptive approach to what frameworks you should use. PyTorch recently, really just in the past year, has risen to at least parity and perhaps even surpassed some of the other frameworks, mostly due, in my view, I hope you guys agree, that it's just so readable. It has a couple of technical features that are really nice, but when I started with PyTorch in the beginning, I just thought, I can read this, I can share it, I can work with my colleagues and do things that I was not able to do with other frameworks. Now, the middle layer, of course, is SageMaker, and now with the advent of SageMaker Studio, we have a truly comprehensive approach to doing machine learning, from the labeling that's required in the beginning to deploying in the cloud and also on mobile and IoT. And then, of course, the top layer of this cake are the managed services where we've taken the data, we've taken the algorithms, and we've put it together, where all you really need to do is begin using the endpoints in the way that you find best for your purpose. So I want to start with a couple of basics. First of all, when you're using SageMaker, you're also, in part, using what we call the deep learning AMI. AMI stands for machine learning image. I'm going to do a very brief demo on how to bring that up and use it. But the reason I point it out is it is a full set of, it's a full set of products for deep learning, for machine learning, that is managed as a product. What I mean by that is every 2 weeks, I believe, is the cadence. A new version of this AMI comes out. You can track it in the machine learning blog. Please do. And when you start up a SageMaker instance, it's inheriting a lot of that good work. Then I'm going to take a look at what are the fundamental tools that we use in SageMaker to deploy our training in the cloud and our inference for hosting. And that is really our estimators. Now, when you look at this code right here, what you'll see is, you know, the word estimator, you've got a role in there, an instance type. What's actually happening behind the scenes is the SageMaker SDK is helping you write a Docker container. Now, when you go to fit that data then, you're actually going to build the Docker container and then submit it to another machine in the cloud that's going to go train that data or then host that system. I'm going to demonstrate that as well, but the fundamental takeaway here is to know that Docker and really S3, because usually your data is in S3 that you're using to train, are these two fundamental foundational components that help enable SageMaker to be the leading IDE. Last but not least, I'm going to demonstrate how you can actually use your own laptop using a feature called SageMaker Local, so that you can use an IDE like Visual Studio Code to develop code on your laptop, but then train in the cloud and deploy at endpoints in the cloud as well. Last but not least, I want to mention briefly PyTorch Lightning, which is another tool that's being used to help solidify the code that you don't need to change when you're doing nuanced changes to building deep learning models, and really focus on the stuff that is going to make your model differentiated. So I'm going to switch over now to my demo machine here. Hopefully I hit the right button. There we go, and I have to start from scratch here, so forgive me while I log in. All right, cool. So when you bring up SageMaker, of course, you're instantly prompted, or more likely, to create a notebook instance. Jupyter Notebooks are the principal tool that we use to create our models. I want to show you that within 5 minutes, you can be running and generating models using PyTorch. I'll just, it's December, so I'll name this notebook December. And I'm going to come down here to the Git repository part of notebook creation and say I'm going to clone oops, that's not it. I'm going to clone the the PyTorch examples repo. I've got that in my code right here to just cut and paste. And when I hit Create Notebook Instance here, I'm instantly going to create a notebook that has PyTorch code ready to go in the cloud. Now I have a pre-baked notebook instance here, and here's the SageMaker browser. I created something in the MNIST data set where I just took the main Py file that's in there and created a little notebook out of it. And all I have to do here is run all the cells, and within, what was that? So if you take out the part that I pre-baked, the 2 minutes to start up the instance, I'm already running genuine PyTorch code and training it in the notebook. Now the question is, how do I get that into the cloud? Well, before I just go straight to the cloud, what I'd like to do is actually show you how to bring up an EC2 instance with the deep learning AMI. Now, SageMaker is the best placed and the safest place to create machine learning models without question, but sometimes it makes a lot of sense to create an EC2 instance from scratch. If you click on Launch Instance here, I'll push this over to the side, and over here on the left you'll see AWS Marketplace. You have a choice of Amazon machine images. Now these are all the things that you need to create the operating system, all the drivers that connect with the GPUs, etc. And also, if you type here just deep learning, oops, you have to spell it correctly. You'll see that we have some AMIs that are specially made that have a number of components built into them. Let me just select this here now as my machine learning image. And you can read this in some detail later, but here are all the tools that are built in. Now, if you've ever tried to build this on your own, in other words, take your own machine, whether it's Linux or Windows, put in the drivers for NVIDIA, for CUDA, for your framework of choice, whatever, it's maddening. Here it's all done for you. This is a managed product at AWS. Like I said, it's updated frequently. My machine, I have a laptop that has an NVIDIA card in it, and I spent $3 grand on it just so I would have that. Worked perfectly in August. But today in December, it doesn't work anymore. Why? Because these dependencies keep changing. I mean, now we've got PyTorch 3.8. That's just one thing. The NVIDIA drivers change. Here, all you have to do is select that AMI, press Continue, launch this instance, and I'll come back here just a bit and show you that I've got one running here right now. Now, the way I tend to access my EC2 instances is I just use this little helper code that's you can get when you just right-click on this. But just to speed things along here today, I have some terminal windows here that are, oh, well, it looks like this one's already running. And what I've done is I just went into that system, and I brought up a Jupyter browser there. Whenever you do that, I'll just make this really big so everyone can see. It gives you a URL that you can use on your own machine. On my other window here, from my local machine, I tunneled in through SSH to that machine. Now I can just go back to my browser and connect through that tunneled connection. And here I am now. I'm in you see the standard, the default Jupyter notebook. I can tell that because I don't have SageMaker examples up here. And I'm looking at code that is on that machine. Now, one of the things that I have up here is PyTorch Lightning. One of the reasons I like to point out PyTorch Lightning is it is a standardized way of delivering code for NERPs. It also has those features that I was saying that make it really easy to focus on the code that you're changing, the model that you're actually changing to make your model unique. One more thing that it does that's really useful and helpful is to take the size of your nodes in your deep learning model and actually use something other than 32-bit. It's called partial precision. So by default, when you create a deep learning network, you're going to have 32-bit sized nodes. You can actually do 16, 8, and even 4-bit precision. Now, that opens up a lot more nodes in a smaller memory space, but it also has this effect that Dropout kind of has, where it can actually make your model a lot more efficient. Okay? Now, one more thing before I hand it over to my colleagues here to talk about is SageMaker Local. Now, I mentioned that there's a feature in SageMaker called SageMaker Local where you can specify when you are deploying your system that either your instance type, let me make that a little bit bigger so that you can see, is either one of our EC2 instances in the cloud. In this case, it's an AIM4 extra large. But were I to change this in the estimator to local, like that, it would train in my notebook. Or if you do a pip install SageMaker on your laptop and you download those containers, you can also have the same functionality on your machine. Now, that's really helpful for sort of the busy work that you have once some code is in production. You have a small sample set of data on your local machine. You want to make sure that all the bugs are out. This also works for notebooks that you launch in the cloud. But here's the virtue of this particular feature of SageMaker. Each of the components in SageMaker, whether that's ground truth, the notebooks, the training or hosting systems, are designed to work independent of each other. And when you take advantage of these features for your workflow, you can do something like this. When I run these cells, let me just see if I can run the whole notebook at once. Run current file. Oops, I picked the wrong one there. Just give me a second here. There it is. That should run the entire file in my Visual Studio Code here. What's going to happen, oops, it looks like I might have typed a little error in there just as I was running this. That's the beauty of live demos. I'm just going to run these all one by one so I absolutely ensure that I fit this. And here we go. So fit is, like I said, it's that command. I don't know why I'm getting errors here. I must have a typo. So the short story here, I'm not going to debug live, is that once that gets to the fit command, I can come over here to SageMaker, go to training jobs, where literally like an hour ago I did this and it worked, and you'll see that the job is actually training in the cloud. So you're on your laptop, you're using Visual Studio Code, not even a Jupyter notebook, and you're training in the cloud. So those are the features that I wanted to highlight from SageMaker and some of the things that you can do with PyTorch. And now I'd like to introduce Michael from Facebook to tell us what's new in PyTorch.
All right. Thanks, Chris. So, hi everyone, I'm Michael. I work at Facebook on PyTorch. And I'm here to give you a little bit of a whirlwind tour on what we've been working on lately, what are the newest features in PyTorch, both in terms of the core library, but also the surrounding ecosystem around PyTorch that enable you to do domain-specific model optimization, domain-specific learning, and all other sorts of things with your models. So what is PyTorch? I assume because you came to this that you kind of already know what PyTorch is, but I can talk a little bit about what it started as. It started as basically a GPU-accelerated tensor library with an API relatively similar to NumPy. One thing that we observed with the old Torch that was written in Lua was that people really liked the imperative style of neural network construction that Torch gave you. And we wanted to bring that to Python because Python is sort of the lingua franca of numerical computing and scientific computing. So you can see here the way that a graph is defined in PyTorch is very similar to regular Python execution, right? You define your operators. You can use overloads, operator overloads like this plus operator, and a graph is defined based on how you ran it. So we also added a number of services on top of the base tensor library. In particular, the thing that made it very useful for deep learning is that we added a tape-based autograd system. It composes well with the imperative style of PyTorch, and it essentially allows you to take gradients and compute gradients with respect to your loss very easily with the simple call to backwards instead of doing sort of a symbolic differentiation step. This also makes it a lot easier to use things naturally like control flow, if statements, loops. So your code really looks more like Python code. What Chris alluded to when he said PyTorch tends to be very, very readable, it's because it just looks like numerical Python code. So since then, PyTorch has evolved quite a bit from the original sort of structure of it. We started with a dynamic neural network library that supported tensors and autograd. But since then, we've added both eager and graph-based execution. So for when you need access to the full structure of the graph in order to properly optimize your model or deploy it. We've added distributed training. We've added other hardware backends besides just GPU. And maintaining the idea that we ought to prize simplicity, imperativeness, explicitness, over sort of doing things magically for you or making the overall library very complex. Our goal is for model code to look very simple, and our goal is to always be sort of understandable, and we evaluate every new feature on that basis. So I'm going to talk about a few of the new features we're working on and have released in PyTorch 1.3. So if you download the deep learning AMI from SageMaker, you get all of this because they've always provided an up-to-date version of PyTorch for your usage. So the first thing we've added is support for mobile. So this is one of the most commonly requested features for PyTorch. It allows you to do an end-to-end workflow from eager mode, where you just define your neural network in Python, to deployment on iOS and Android without a need to convert to another runtime with different semantics or like a different format. It's the same all the way through. If your model as executed from Python will be precisely the same as your model executed on a device. So we wanted deploying to mobile devices to be as natural as deploying to any other device, server or otherwise. And we support any model that is torch scriptable, and I'll talk a little bit about torch script as an enabling technology later. And out of the box, we've provided pre-built binaries for iOS and Android with support for 8-bit quantized libraries, so QNNPAC and FPGEM at release. This allows you to sort of shrink your model so that it runs more efficiently on device. So another thing we've released in 1.3 is support for quantization. So this goes very well with mobile because it's a very important component of running on mobile. But it's also useful for server-side applications. So quantization refers to a technique where we take the floating point weights or activations, and we essentially make them into int 8 most commonly, or even int 4. People have done all sorts of different things. And essentially, it leads to both more compactness in form of memory usage, but also speed-ups in the total inference time. And these are quite substantial often. They're integer factor improvements. And as you can see, we support out-of-the-box sort of a fairly explicit way to do quantization. You just you write quantization.prepare and you pass a model, as well as a quantization configuration if you want to customize which modules are getting quantized and which aren't. But by default, we sort of quantize everything that matters. And then you just write an eval, and you actually run the model a few times to calibrate the quantization statistics, your scale and 0 point. And then you just convert your model. And this essentially quantizes all the weights. And it's a key component of making PyTorch work well at production scale because it's a fairly common optimization technique. Another thing that we've been working on is named tensors. So this is a great example of what we can do when we prioritize the sort of core usability of PyTorch as a library and collaborate with the community and other researchers to work on new features. So this was initially proposed by Sasha Rush at Harvard, who is a core user of PyTorch from the very early days. And he proposed named tensors as a way to get information that you typically like encode in comments or don't encode at all, and get it in the code directly, get it checked at runtime. So you can specify, these are the channels, this is the width, and this will be, any of your transformations and operators will check at runtime that these remain consistent. So we're launching named tensors with 1.3. It'll be out of experimental in a coming release 1.4. And enables cleaner, better code that more directly expresses your intent. So we should also take a look at TorchScript. So I mentioned it before as one of the foundational technologies that we're investing in order to support PyTorch at production scale. This is essentially a way of getting a computational graph out of a PyTorch model. You get Python out of the process, you have access to the full program, so you can use optimization techniques like quantization or simply algebraic simplifications like common subexpression elimination or dead code elimination. So as you can see, the workflow is pretty simple. You define a torch NN module. So if you've ever worked with PyTorch, this should be very familiar. Here we specify a single weight, and we have some state. And we define a forward function. You instantiate said module, and you just pass it to TorchJIT script. And what that function does is essentially runs a compiler that parses your Python code and turns it into TorchScript, which is a format that we can understand and an intermediate representation that is more tractable to optimization. So there are a couple things to note here. We try really hard to support Pythonic language constructs. Typically when we talk about graph-based machine learning frameworks, you think that, okay, now I have to sort of fit my ideas around the specific kind of domain languages that are provided to me. But here, an if statement is just a Python if statement. A list can be represented as a list. You can append to the list, and all side effects are sort of preserved. Loops also work. And you can just call .save, and you get a serialized representation of your model. You can then pass that to mobile for deployment. You can then run quantization on it, et cetera. And the counterpart to TorchScript is the PyTorch JIT, which is an optimizing just-in-time compiler for PyTorch programs. It consumes these TorchScript programs, and they're sort of represented internally, as you can see here. The structure is a lot more regular. Everything is statically typed. The control flow is structured control flow. And this allows us to do full program optimization. It's also not just for inference. This seamlessly supports auto-differentiation. So we can define sort of symbolically differentiable subgraphs from this graph and use that for training as well. Backwards will always give you the correct result, and it sort of seamlessly interoperates with control flow and the default autograd engine for PyTorch. So those are the new features that we released recently in 1.3 and are going to be improving in 1.4. And now I'm going to talk about some new libraries and what highlights we have from both the community and also released by Facebook as well. So the first is crypt10. At Facebook, there's been a huge amount of interest in pushing forward privacy-preserving machine learning techniques. And the challenge is to provide the same value that PyTorch gives you while protecting the data used to train models. So with 1.3, we released crypt10, which is a platform in PyTorch for research in machine learning using secure computation techniques. We aim to enable machine learning researchers who are not cryptography experts to experiment with models using secure computing techniques and to get a realistic view of what's possible, what's difficult, how efficient these techniques. And as you can see, we deeply integrate and leverage PyTorch in doing so. We closely followed PyTorch design principles. So a crypt tensor is basically looks and acts exactly the same as a regular PyTorch tensor. Similarly, you can just add two of them. If you call common torch functions, it'll handle all the sort of encryption under the hood. And so you have sort of seamless interoperability with the sort of base PyTorch library. And we're hoping that this ease of use lowers the barrier of entry for machine learning researchers and developers who are already familiar with PyTorch and the abstractions that it provides. Similarly, with the increase in model complexity, model interpretability methods have become very important and is a substantial area of interest both in the community at large and at Facebook. So model understanding is a really active area of research, and we also have a number of practical applications across industries using machine learning. So we're releasing a new library designed to make interpretability algorithms accessible to all PyTorch model developers. It's called Captain, and it allows you to interpret outputs with respect to inputs and layers, and neurons with respect to inputs. It provides an interactive visualization tool that helps you understand and debug the model predictions that you're getting. And finally, beyond new libraries that add sort of core functionalities to PyTorch, we are also supporting a number of frameworks that allow you to use PyTorch in a specific domain to solve your specific business problem. So the first of these is Detector 2. We open source this with 1.3 as well. It's the second generation of Facebook AI's system that implements state-of-the-art object detection algorithms. So as I mentioned earlier, it's used in the portal, and it's also shipping in several other Facebook projects that need object detection and segmentation techniques. So improvements over Detector 1 include support for the latest models and new tasks. We've increased the flexibility to aid computer vision researchers as well as people interested in deploying for production. And we have sort of baseline improvements in maintainability and scalability to support our production users as well. The next framework is FairSeq, which we've extended to support sequence-to-sequence applications for speech and audio recognition, as well as what we typically did, which was language translation. So these extensions allow FairSeq to enable faster exploration and prototyping of new speech research ideas, and are also used in production today. So these are some resources like our social media stuff and our website. A lot of these features are still works in progress, and we'd love your feedback in using them. If you file an issue on GitHub for any of these, you might see me commenting on it. And so we'd really appreciate any feedback on new features as you try them out. And now I'm going to hand it over. Sorry? Oh, that's unfortunate. Well, I assume you can find us on Facebook, or if you go to github.com/PyTorch, that's mostly where we hang out in terms of PyTorch development. So thank you, and I'm going to hand it over to Alex to talk about how they use PyTorch at Autodesk.
Hi there. So my name's Alex O'Connor. I work for Autodesk. I think I'll start by talking a little bit about who we are. So our products range from construction, manufacturing, and media and entertainment. Anytime you see a major construction project, a large building, a high-performance vehicle, or some sort of 3D animation in games, in movies, there's a good chance that one of our products has been involved in it. We have 30 years, nearly 40 years of experience with a variety of these tools. Some of our most commonly known products are things like AutoCAD and Revit, and newer products such as Fusion 360 in the 3D printing domain. So we have millions of users. They are all around the world, and they're an interesting group because they are highly professional, highly expert people who work in very complex domains. So that means that we get thousands of queries and thousands of customer questions every month. And those questions range in enormously in the types of questions that they are, in the complexities of the solutions that are required, and even in the level at which we can address the problem for them. So this really does range from relatively straightforward tasks, such as how do I download a particular version of a software, how do I get an extension, how do I change a language pack, all the way up to one project which one of my colleagues discussed with me, which is where they were doing flow analysis of a structure, and it took 2 days for the HPC environment to just resolve the file before they could even begin to solve the problem. So we had real problems in trying to understand how we would support those people. And that creates a challenge, because if you try, even as a human, to understand the full range of complexity of the terminology, the support domain, the knowledge domain, and the professional practice that's involved, it's simply not possible. And very often these technical cases come in, and I could spend a week on Wikipedia reading the articles and probably still not come to an answer as to what they were actually talking about. So that creates an extremely complex problem for our support teams, and it creates an extremely complex problem for us to resolve. And thankfully, that means they needed data scientists, so they hired us. What's interesting about this is that we fundamentally have to understand that we have a language problem here. We have a pattern matching difficulty. And this quote is about how people use memes on the internet, but it's true about how people use technical language. It's how people use keywords. It's how people use professional practice and language in a way that is important to them. So even when we see it appears completely incoherent to us, even when it's something that is totally opaque to the layperson, it is nonetheless something that we can learn patterns from and that we can take advantage of and that we can scale and automate and operate on. So really, when you think about this domain, we like to think of it in the context of natural language processing. Really what you're asking yourself is how do we take this set of words, this set of repeated tokens, and represent the concepts, the context, the meaning, and all of those words to a computer in a way that we can act on it. And that's a problem that's been with us for 70 plus years and is a problem that will be with us for another, I think, as long as we are all speaking to each other. But we've made enormous gains in the last decade from the fact that we've been able to leverage the sort of technologies that Michael's teams are developing and the sort of infrastructure that Chris's team is deploying. And so we have this essential challenge with language data. The words don't arrange themselves in neat ways. People play the language game, so they use metaphor, they use simile, they use contractions, they indicate typos, and so we need to be meticulous in how we prepare data to train the models and how we use that to advance things. So just taking a very simple example, we can take this sort of reduced complexity version of what you might think of as being the sort of typical data that most people will be involved in seeing if they are in this support natural language environment. So we have a customer, they submit a problem, they say something like they're using this particular Revit product, which is in the construction domain. They have a serial number, and they also are not terribly good typists. And this is the sort of typical data that we get. This, in fact, is what you might call a laboratory or a spherical cow version of these things, because we rarely get users that are this explicit or this organized in the way that they state these things, because, frankly, their time is valuable and they don't necessarily lay these things out. But we can imagine that this is a pretty straightforward way of doing things. And part of the frameworks that you might want to use when you're addressing this is that there is, in fact, a PyTorch text framework, or we use the Spacey framework, to extract these key phrases and extract this boilerplate text at the top, these pieces of the form, from the body of the text that we're most interested in. So fundamentally, our task is to take this body of the text and ask ourselves, which team of agents should fix this problem? And in doing so, we can find an enormous saving in time, an enormous saving in resolution time for the customer, an enormous saving in time for our teams, and an enormous cost saving in getting that to the right place at the right time. Plus, we don't have to keep people on hold. We don't have to keep people waiting for an answer. And in a professional context, time is money. Waiting to resolve a problem that is a big one for an architecture firm who have a project on the line means that there's potentially millions of dollars in getting this correctly done. So that leads to our team and our mission and our fundamental question, which is, how can we help our customers ask questions they need answered in their own words? So we want to get back to this situation where, to the minimum extent possible, our customers should not have to learn our terminology, shouldn't have to learn how we think about our products, and instead, we should be able to meet them more than halfway along the way. And that means that we need access to the state-of-the-art in machine learning. We need access to rapid deployment so that we can put those models out there and when they break, fix them and replace them with ones that work better. And we need to be able to share things amongst our team and amongst other people in our company, because we're all working on these complex terminological collections. We're all working on large volumes of data, and we don't want to be in a situation where everyone is downloading the data multiple times, processing it in different ways, and wondering why they get different answers. So the technology that I'd like to talk about today is the transformer. The reason I'm choosing this is that it is buzzword compliant in the most extreme way. It's the most kind of interesting thing that's happened in natural language processing in all of 2 years. And what it does is that transformers represent a step change in the performance of natural language processing because they allow us to do more with less in a way that is revolutionary. And the three main kind of technologies I draw your attention to are Hugging Face, who are a startup that are in the natural language understanding and virtual agent environment, but also are amazing contributors to the open source community. Fast AI, who have another set of transformers, another set of methodologies for doing NLP, and PyTorch, which for us is the domain of the framework of choice for a lot of this work. So why do we choose why do we choose PyTorch? Well, there were really three things that we found to be the reasons for this. And I sat down with some of the members of my team to really think about this because we wanted to be sure of what we thought were the things that would make it compelling for you to pick up PyTorch in what is a very competitive and very noisy marketplace right now for your attention. I think number one was the interest in the fact that it gives us access to research code. So there have been multiple papers over the last couple of months which have shown that PyTorch gets the most mentions in the major venues, especially in natural language processing, and that it provides direct access to these sorts of insights that the research community has given us, both from the commercial research and from academic research. And the ability to get from a paper to a deployed endpoint is an extraordinary thing that even 5 years ago I think would have been unrecognizable. The second feature is the one that I think Michael talked about a lot, which is the intuitiveness of the interfaces. There's really one way to do most things in PyTorch, which is a great advantage, because if there's 12 ways to do something in a framework, you can imagine that most developers will come up with a 13th and get it wrong as well. So for us, it's very useful to be able to very natively approach the problem and be pretty clear on why you have gone a particular way down that route. And finally, new features, the integrations as they come along, eager execution, and all those sorts of things make it very attractive for us to be able to take advantage of those things as PyTorch develops. So what is a transformer? The key understanding about a transformer is that when you think about language, there are a couple of different tasks you need to be able to do. The first thing is that you need to be able to understand and organize yourself in the actual language itself. So there's a whole higgledy-piggledy mess of words and tokens that are kind of flying around, and the model needs to make sense of that before it can address your question, which is, which support team should I refer this support case to? And so for us, that meant that when you were training these models, these more naive or more shadow models in the past, you had the problem that trying to learn both of those things at the same time was essentially impossible, or led to a great deal of confusion and overfitting and a great deal of missing of important nuance in the models. So what we did was, not what we did, excuse me, what the research community did was realize that what you probably need to do is learn English or learn the language that you're trying to learn before you go at the specific task. And in that case, what we need to do is we need to have a multi-objective approach. We take a large amount of data, hundreds of gigabytes of text, and we just read it. And what we do is we learn multiple simultaneous objectives at once. So we learn, in the case of BERT, you learn a masked objective where you try and predict the word as it is. You mask out a random number of words in the sentence, and you try and guess which word should be in there, with the objective of, over time, learning these multiple objectives gives you a higher performance on everything. So the system has learned a sort of a general model of the language before it even gets down to this task of your specific system. And then we use the concept of transfer learning to take that large general model and put it to our specific use case. And that means that you can use it for text classification. You can use it for language generation. So the GPT-2 transformer has got a lot of attention because of people using it to create all sorts of things like poetry and movie scripts and all sorts of other things, and in machine translation as well. And in all of those things, we have that situation where it is, if not state-of-the-art, then very near, suitable for a wide number of tasks. And what's nice now is that we know that it works pretty well in Chinese, and the exquisitely named Camembert demonstrates that it works very well in French as well, which is, I think, for other colleagues of yours. Very briefly, the intuition behind this BERT model that I'm going to talk about is the idea of multi-headed self-attention. That means that I'm going to look at the whole sentence at once, and I'm going to try and infer the importance of each token relative to the others from multiple different perspectives. What that means is that I don't just take the single context of a token one at a time or just look backwards. I look across the whole sentence all the time in multiple ways. And that gives me my subtlety, my nuance, my ability to manage it. If you want to train these from scratch, you can go at it with the Torch NN modules transformer, which we're very grateful for. One thing I would say about this is that this is not at all limited to language. Transformers are an excellent way of doing code generation. They're an excellent way of doing a wide variety of other tasks. Anything where you have about 100 billion instances, I would recommend you have a shot with a transformer. But also check your credit card limit before you go at it. So how do you use a transformer? This slide is painfully out of date because I think I wrote it 6 weeks ago. And so 1.6 billion parameters is now, that's amateur hour for transformers, but it's still a relatively large model. Trained on multiple objectives, self-supervised. The important thing about this is someone else trained it. So Google trained it, or Facebook trained it, or Salesforce trained it, or OpenAI trained it. You can immediately take advantage of their millions of dollars of investment and straight up start building your own model. So you train that pre-trained model from someone else. You optionally decide that you want to tailor it. So for our situation, we have a situation where we have a lot of language that is not used in the conventional way. The meaning of words is based on the fact that we have architects or we have engineers talking about things. So we might want to slightly teach not just English, but Autodesk English to the general model. Once we've done that once, it's repeatedly available. We don't need to do that again. And then you fine-tune the model yourself. So then what you do is you say, OK, we have this general language model. It does all these multiple objectives. It knows English. It knows grammar. It knows Chinese. It knows all these sorts of things. So what we do is we attach a new head to it, and we say, OK, now instead of doing all those old objectives that we were interested in, we want you to predict a support label. Tell us which support team is interested in this, or we want you to generate the next sentence that comes after this, or any number of other objectives that might be interesting along the way. So how does this look? One of the nice things about the BERT model is that it's really simple to produce the data. All you need to do is reformat it into the format where you have the words separated by 2 tokens. And in fact, this is how it looks when BERT itself tokenizes that. And you'll notice that there are these hash mark symbols. And what those represent is subword components. So the BERT has learned not just whole words, but parts of words in a somewhat random way. But nonetheless, you can see here that we have our sentence, I can't install Revit 2019. And it's split Revit into 2 tokens because it doesn't know the product name on itself. So BERT can take advantage of that. It can take advantage of these subwords. It means it isn't dependent on the conventional approach. So how do we attack this problem from a practical perspective? Step 1 is to decide if you want to have a base or a custom model, if you've done this fine-tuning or not. I recommend just starting with the base model if you've nothing else. It's free and relatively easy to get. And I'm taking the adaptation of the code here from the Hugging Face transformer library and this example run glue model. So glue is a large evaluation data set, which itself is now out of date because, as I said, 6 weeks is a long time in machine learning. And we preload the files from S3 and adapt the data loader. Those are the only 2 tasks we need to do to make this available on SageMaker. So for this may be familiar. This is almost exactly the same code as Chris had by happy coincidence. And what we do here is that we have a slightly different set of arguments, but otherwise is very much the same. In this case, I'm using a P38X, but apparently today, the AWS team managed to train the base BERT model in 69 minutes on PyTorch using 192 DN instances. So if you're really in a rush, you can do this much faster. But we use this sort of a model. We use this approach. We use Framework 1.0. Apologies, but that's a dependency from the transformer, or the transformers model. And then you can see as the same thing again. We just have an estimator and a fit, and we just train the model as per normal. So almost identical here, except for how we do these things. One of the interesting things and one of the best features from our perspective is you can just include a requirements.txt file with your Python file for your estimator, and it will pre-install all of this data for you. So it'll pull down all of your libraries for you. It'll pull down the transformer library, so you get all of that stuff without any sort of management of the dependencies in a complex way. All the magic happens in the hyperparameters as normal. You have to specify your labels. So these are 7 different support labels that we can use. You can see the one on the right is technical support, and I won't get into what the other ones are. And then the only other things you need to know about are this is your base model. In this case, we're using the BERT base uncased. And we just have to make sure that we lowercase everything because of that thing. So make sure those things agree with each other. BERT looks at a fixed sequence length, so you can set that sequence length. It's trained at 512, so you can use anything less than that in whatever way you like. And there are different masking schemes for different transformers there, but that allows you to speed up a little bit if you know your sequences are shorter. Sequences count subwords, though, so be careful with that because those double hash ITs and things like that will pop up and can sometimes be slightly longer than you expect. And obviously then the normal things that you know, batch sizes, learning rates, and number of epochs. And typical values here are, as you would expect, between 1 and 8 epochs, and something along the line of the start at a lower learning rate and go upwards. Sorry? Yes, that's what that sequence, that's what the max sequence length does. That is the maximum width of the tokens. And what it does is apply a mask to that to pad out automatically if it's not in that space. So then we just load the model, load from pre-trained, pull it from S3. You need to load your tokenizer as well because you might have a specific vocabulary there. One nice tip here is that you get some, in BERT you have some unused tokens up to 1,000. So if you have custom tokens that you would like to use, you can replace those in there, and in your fine-tuning you should get access to that, which is a neat way of taking advantage of the way BERT has been structured. And then in this case, we attach the head in the second line there. BERT for sequence classification is the tool for creating text classification models, and it's very straightforward apart from that. And in this case, the arguments that you see there are fairly straightforward. One is a model path, because this is SageMaker. That can be anything that SageMaker can access. The number of labels just comes from your training data, or from your hyperparameters. And then from TF is sometimes you might want to use a TensorFlow compiled model, and you can do that in this context if you want to use the truly based models or some other things. When we run the training, typically the way these models work is you warm them up. So you give them a higher learning rate for a certain amount of time, then you optimize after that. So we found that 100 warm-up steps works. Don't ask me why. Maybe it's because it's a nice round number. You can also use proportional warm-up if you prefer. You can change the number of steps. You can do all that sort of work. All that stuff is a good way of testing your model, but I would do that after you've done other things with epochs and things like learning rates. I would also say that one interesting thing here is that it's been observed that sometimes transformers just fail. So sometimes they just don't initialize well, and you sometimes need to just restart the training and it'll work better the next time, and maybe change the seed. So it's all that lottery ticket stuff about whether or not you've picked the right initial parameters. And so sometimes they just don't work, and that's not just an excuse. Apparently it's true as well. And then we use the AtomW optimizer. That's all been very neatly reorganized. And in this case, we're reproducing the paper for BERT, so we have correct bias off, but you can change all of those things as you see fit. So that's basically how you would use BERT. Go and do it. You can have state-of-the-art or near state-of-the-art text classification, probably in a couple of days, and certainly leveraging an amazing amount of research and work from everyone else. Oh, I should say also, that's the other key thing about this. Your label data set for classification doesn't need to be remotely as large as the full data set now. You can work on far fewer examples because you have this ability to learn from the baseline model. So just a few other things about how we use this. One thing that we do is we use everything. We're very SageMaker focused in our team. We have a shared space on EFS that we put data, we put our analysis, we put our notebooks. We do an awful lot of code sharing and visualization through it. We put our pre-processed data sets because of the large amount of work that can often be done to have to pre-process a data set for language. We use these custom profiles for our SageMaker instances, and we frequently back up because there's not a lot of access control on a shared EFS, and we often worry about someone hitting the delete button by mistake. But for us, it works very well. It gives us this global scratchpad that we trust our colleagues with. And we all work in the same office, so it's easy for us to shout at each other if we get it wrong. You know? What do we share? We share all the data that we've cleaned, all the pre-processed information, all the enriched data, and then a wide variety of the utility models. All of those things help us a lot because they allow us to get much faster at iterating through models, much faster at handing off code, and much faster at repurposing specific models for things. And where you have things like these fine-tuned models, they're extremely useful to be able to share those in a rapid way. We're also experimenting with the use of model services. We attach an endpoint, or we use a batch transform, or we just put up an EC2, and we have a ULM fit model in this case behind it that allows us to have an embedding service. So people can send text, get back a fine-tuned embedding model that allows them to consistently and transparently make use of that data. So that allows us to offer this service to people in a way that is very much transparent to them and very much invisible as to all the complexity and crying and debugging that was happening in the background along the way. So I would recommend very much thinking about these kinds of ways of how you deploy the intermediate models as well as how you deploy the final products as you go along with this, because you can share and gain a lot of infrastructure value, especially natural language processing, from doing this sort of work in a way that is open and shareable and well documented. So just to conclude, I think the key thing for us is that we find notebooks to be a very natural way of doing data science. We're very encouraged to see how things like the SageMaker Studio will develop this further with the ability to model a multiplicity of different concurrent experiments in a way that we can actually track it. That option of magically changing one thing at a time, which requires an awful lot of discipline, but is a wise thing to do, is something that we think being able to do that in this consistent way is helpful. We get a lot of value from the fact that we can have jobs running in the background, jobs running overnight, jobs running for days on these EC2 or SageMaker or all the other instances that we have in a way that makes it very cost effective for us, because we can just shut them down when they're done, and because we don't have to give everyone a $3,000 laptop if we don't want to. Or, well, yeah, that's probably not the only saving, but it is particularly one that helps us. And then finally, I think the ecosystem is immensely powerful. We're very grateful to our friends and colleagues across the community at all levels of abstraction here. Everyone who's sharing basic Medium articles on how to do this stuff, all the way up to the people thinking really hard about named tensors or continuous training models or distillation models or all that other stuff. Everything that the full spectrum of that is something that we find immensely powerful and immensely helpful in our work as well. Thank you very much.
So I just have one or two closing comments. First of all, I want to thank Michael, Suo, and Alex very much for being here today and sharing that. The partners at AWS and the partner network are very important to us. It is a high priority for AWS consistently. The last thing I want to leave you with here is just a set of resources. Let me push the button. That will help you with, let's see if I can get this right here, that will help you find some of these PyTorch resources that are a little bit hard to find once in a while. There we go. So that's it. So once again, thank you very much, Michael and Alex, and we'll be around for questions afterwards. Thank you very much for being here.
All right.